2018 AS Physics Unit 1, question 6. This is our stars and radiation question. Right, you know what it's going to be. There's going to be a Wien's law part in there, there's going to be a Stefan's law part in there, there's going to be an inverse square law part in there. 3 formulas, make sure you know how to use them. All the constants are given to you. And for this one as well, they give us a spectral intensity graph and ask us to talk about it, basically. And they offering 6 marks, right? So you're going to be needing to write 4 to 5 very coherent aspects of this graph to get those marks. So let's just read through what I've put here. So obviously the wavelength at peak intensity can be used via Wien's law to determine the surface temperature of the star. That's probably going to get you 2. The power emitted per meter squared can be calculated using Stefan's law. Right, that's going to get you another mark. The colour of the star can be deduced from the wavelength of max intensity. Don't forget, 400 nanometers is bluish, 700 nanometers is reddish. Maybe I should have mentioned that. The spectrum itself allows us to identify elements from looking at specific wavelengths in that star's atmosphere. This is a line absorption spectrum because it has black lines on the spectrum there. And then finally, the spectrum is produced by a continuous passage of radiation or photons through space, right? So this is 2018. This could come up in 2023. So make sure you just learn this off by heart, okay? It's not difficult. Learn it off by heart. That's how we interpret a spectral intensity graph. Right. And then they're talking about this star. It's the brightest star in the Aquila constellation. They give us the distance. They give us the intensity. And it's a show that the luminosity, right? So you've got to know your inverse square law equation. So the luminosity, we usually write it the other way around, right? We usually have intensity is luminosity divided by 4 pi d squared, where d is the distance between the 2 stars, okay? So I've rearranged this because they want us to give the luminosity, so I've brought that divide by 4 pi d squared up and over as a times. So luminosity is 4 pi, the distance between the 2 stars, there, squared, check units, yep, it's all in the right units, meters, times the intensity. There's the intensity, watts per meter squared, all in the right units. It's a show me, so we know we're looking for that. I chuck those in the calculator and I got 4.14 times 10 to the 27 watts. Happy days. Then calculate the diameter using Stefan's law, right? Given that its surface temperature is 700 Kelvin. Now, a lot of people would have messed this bit up on the exam, but that's fine because they've given you the luminosity here. Right, so they've given you the luminosity, so even if you didn't get that out, you better go and get these 3 marks. The luminosity or the power, don't forget those words are interchangeable, is the surface area times sigma times t to the power 4. Don't forget that's to the power 4. So chuck your numbers in. I've used my exact answer. You could have used the show me answer. Times the area, Stefan's constant, temperature to the power 4. Tidy it all up. Don't forget, we assume a star is a sphere. Surface area is 4 pi r squared. So this area now, bring the 4 pi over as a divide. That gives me r squared. Square root it to get the radius. They've asked for the diameter, so don't forget to double it. Here's my answer, 2.57 times 10 to the 9 meters. Okay, we can't really say, how do I feel about that answer? Stars have a phenomenal range of different sizes. We can't really comprehend what 2 billion meters looks like, right? But double check all your calculator pressing. And yeah, that wasn't a bad one. On to the last one.